So today we have the honor to have Professor Maas to give us a talk on the Nonlinear Tidal Estuaries. And Leo from Royal Institute, Netherlands Institute of Physical Research, which is also known as NIOZ. And he's also a professor at Utrecht University. And so some of you actually know his work. Yeah. So he's done quite a lot, actually, theoretical and experimental, and in his own words, also sometimes field observations are related with fluid phenomena in oceans, and in particular internal waves.
I just had a question of Leo. So Leo, where were you before you went to Texel?
At Utrecht University. Utrecht.
Utrecht?
Yeah. So I did my PhD at Utrecht University.
Okay.
And then switched for a postdoc at NIOZ, and then stayed on at NIOZ. And then
in which department did you study at Utrecht?
In oceanography and meteorology.
Okay.
Yep.
Well, that's a good bio.
It's a nice way of starting with an interacting audience, so please feel free to continue in this way.
And he recently has been working very intensively on this internal wave focusing and interacting with topography, and for example, the tidal conversion or the lack of tidal conversion. So we're going to hear something about it.
Okay, thank you all for being here. I'd like to express my gratitude to PhD student Guido Terra, two master students, Jordi de Boer, Sjoerd Kroeskamp, and a postdoc, Janine Now, who all contributed to the topic of this talk. And I'd like to start with stating my motto. I hope you understand by expressing this why I'm presenting the work that I'm doing in the way I do. So my view is that we as humans, we are sensitive to patterns, and that it's sometimes difficult to discern when we look at complicated observational or actually also numerical fields. And therefore, it's worthwhile to search for simplicity in complexity using, say, simple models. And preferably, simple models that you can actually test by doing experiments, or even more preferable, to test them in the field, because those, I believe, bring understanding. So I hope you forgive me for starting with this pedantic note, right? But this is what my own philosophy is about this, about performing science. Okay, so the topic starts with an observation made more than 100 years ago in a very eloquent study by Honda and colleagues, who observed that the seas around Japan consist of bays which very often display, apart from the primary response, namely the tides, also what they call secondary response, namely undulations, which in some way are related to coastal resonance. And observing many bays, that the sea level variations often have features which have periods in the range of 1 to 60 minutes, so much longer than the surface waves, the surface gravity waves, and also amplitudes of between 1 and 20 centimeters. It seems that these are ever-present features which need an explanation. So I think Honda was right in arguing that the only feature which is persistent over time are the tides. So he was also contemplating that perhaps tsunamis might have generated these features, or the wind, right? But also when there's no wind and when there are no tsunamis, these eigenoscillations are observed. And so, to translate from Japanese seas to my own situation, I'm staying here at NIOZ on an island which, together with the tidal flats around it, may have some similarity to the regions here. And I was also quite intrigued by the question what the influence is of all these tidal flats on the response of the, in this case, the Wadden Sea, so this inland sea. And so that's an issue I'd like to address. Now, there are also new indications for these what I can now call secondary tides, right? They are not really tides, but they seem to be produced by the tides, the secondary undulations. There are also new observations, like for instance the ones from a fjord in Norway, where you see the entrance of the fjord and which there's a long fjord behind it, which shows near the entrance this type of feature in the sea level elevation. So you see a very distinct presence of the tide, but superimposed on that you see these slight variations which have periods of about 49 minutes, much less than the tidal period, amplitudes, in this case of about 10 to 20 centimeters, much less than the tidal amplitude. So at some point you may say, okay, well that may be so, but what is the relevance of this, right? Why should we be interested? And the interest comes actually from the additional observation not only of sea level but also of the currents through the strait. So here you see the speed in the solid lines and the direction in the dashed lines, and you can see that it's very hard to observe what the tidal current is actually. There is a continual change in magnitude of the currents. And so the conclusion seems to be that we should be interested in these minor perturbations to the tide because they have an amplified effect on the currents. Now, why is that the case? It's not very difficult to speculate that the reason is that what's determining the currents is the sea level difference within the fjord and outside the fjord. Now, if you think of the tide outside the fjord is going up, that within the fjord follows, right? And what is relevant for the currents is actually the instantaneous difference in the two levels, right? They may go up like this, but what is important is the difference in the height. That's setting the currents. Now, if you assume that that difference is of course less than the tidal amplitude itself, and suppose it is of the same range as these oscillations which are excited within the fjord because they are eigen oscillations of the fjord, right? And suppose that they are absent these oscillations at frequencies of the fjord outside the fjord, then it makes sense that the currents can actually be comparable, and it may be the reason why you get this enormous change in the magnitude of the currents.
Excuse me, that's in the mouth or in the interior?
This is in the mouth. Yeah. Yeah. Now in the interior, it's actually the currents are quite weak. Yeah. So before looking further into this interesting property, I need to mention that in our field we basically distinguish two types of resonators, and the first one is exemplified by the Bay of Fundy, which we call a quarter wavelength resonator, which has a node at the entrance and maximum amplitudes at the back, and we have a number of them, so we can find higher harmonics of the quarter wavelengths in such a bay. However, if the bay is of a different shape, namely when it has a narrow entrance, like, well, I'm taking here one example from the Wadden Sea, where we have two islands and we have watersheds here, the dashed lines, and so basically this region is filled through this inlet. Then we know that there is a new frequency appearing in this response, which is called the Helmholtz frequency. And this is a frequency which is usually much less than that of the quarter wavelength. It's interesting because it's a frequency very, very close to us as human beings, because it's also called the breathing mode. Right? When we breathe, we suck in air, right, and we expand. And something similar happens with this basin here, right? It's sucking in fluid, it expands, the water level goes up, and then goes down. So you have an exchange of mass through the entrance, and you can absorb the mass within the domain by expansion of the fluid domain. Now we're going to look into this particular type of resonator further because it's it's didactically very simple to understand. But what is going to be said about this can can to some extent also be applied to the other resonators. So I won't speak about those, right, because they're more complicated to deal with, but we'll concentrate on this type of response. And so one last statement I should mention is that you're aware of the fact that the tides on Earth are generated in the oceans, right, and that everything that we see in terms of tides in the coastal areas is a matter of co-oscillation, right? And therefore, it's interesting to wonder if perhaps tidal frequency can get close to one of these frequencies, because then you may expect a strong response, right? Well, it happens that this is sometimes true, like for the case of the Bay of Fundy, but also you sometimes see a strong response when it's not true. And this is raising interest in this issue.
Excuse me, your last statement, sometimes you see a strong response?
Yeah, even when this resonance condition is not satisfied. Yeah, and that's puzzling. Okay, but it's at the same time of interest to us. So let's look at the basic model of a Helmholtz resonator. It's another analog is when you have a bottle and you blow on it, that you hear a sound, right? It's also due to the presence of this resonator. So what is it about? We have a basin here, which is communicating through a sea strait to the open sea by exchange of mass. And it's interesting to consider that this basin has a relatively small scale compared to the wavelength of the tide. Because in that case, you can argue that when the tide enters through the sea strait, that since it is so small, it's progressing through the basin almost instantaneously. And because of that, you can actually describe this response of the basin by one state variable, namely the elevation within the basin, right? And it becomes a function of time rather than a function of space and time, like we're usually forced to consider, right? But it being a function of time only, of course, has an enormous advantage because we can describe it by an ODE rather than a partial differential equation. So what is this ODE? Well, if we assume that the walls, the side of the boundary of the basin has vertical walls, then it's obvious that the excess volume that we can define, so that's the amount of volume in excess of the volume that's present at mean sea level, that's simply the product of the cross-sectional area, A0, times the height of the sea surface elevation within the basin. Right, so this is the volume, the excess volume, which is present in the basin. We also have this mass conservation law, or rather volume conservation law, which tells us that the volume of fluid changes due to that which is being transported inwards, meaning the velocity through the strait multiplying the depth of the strait, and we assume that for the moment to be the same as the depth of the basin, and multiplying by the width of the strait. Right, so this is quite direct. Then, when we want to know what the velocities are in the strait, we have to integrate the momentum equations over the length of the strait, so between 0 and minus L, and we get a finite difference version of the pressure gradient, which is due to the height differences between the external tide and the tide within the basin. Right? It's very, very straightforward. Here you see the classical minus g d zeta dx, except it's now in a finite difference form because you have integrated over this channel. Right? So differences in fluid height drive a flow. In this case, it's fairly simple to multiply this second equation by hb, by these two constants. So we get GHB here, and to work towards an equation for the sea surface elevation, so we conclude from this first expression that zeta is V over A naught. So we get the equation which looks like this. We get a oscillator equation which has the Helmholtz frequency defined here as the relevant frequency. And you see it's a driven linear oscillator. nothing spectacular, okay? However, if we now consider that this is quite a stringent assumption, if we think of one of the first images that I showed, right, which showed that there are extensive tidal flats present, right, it's nothing at all like having vertical walls, right? So it makes sense to actually object against this assumption. So we are going to change this and say, now assume that the depth is not uniform, right? So we have a cross-sectional area which is a function of height above the deepest part of the basin. We still assume that the water level rises and sinks in unison, but now we have a sloping boundary. And then we deduce that the volume of water is simply the integral of the surface area which is covered at a certain height, integrated from mean sea level to the present sea level elevation. Right? This is like a generalization of the previous result. It was A0 times zeta. And, well, to continue, we should now regard zeta as a function of V or V as a function of zeta. So that's why I have a dependency on the volume here in this momentum equation. So, if we now combine the two, we see that we get this equation. We still get the same forcing due to the tide at sea, but we see that we have a restoring force which is now a nonlinear function of V. Zeta is now perceived as a function of V, or right, in this expression. And so the question is, what is the consequence of this? Well, in advance, we can tell that we have to do with a forced nonlinear oscillator, and this has a whole world of connotation with it. Because we know about nonlinear oscillators, like for instance nonlinear springs or nonlinear pendula. Like the real pendulum, the physical pendulum, right, is a nonlinear oscillator, right? It has this sine of theta restoring, right? And we know that because of that the pendulum has interesting dynamical behavior. If you force it at its eigenfrequency when it has a small amplitude, you may be able to let the amplitude increase of the pendulum, right? But since it's a nonlinear oscillator, you get a detuning. The eigenfrequency is a function of the amplitude of the oscillation. And so, when you don't change the forcing frequency, you're going to actually damp it rather than accelerate it. So this world of connotation, right, is behind the observation that we have to do to deal with a forced nonlinear oscillator.
I just ask quick, there's no friction in this.
Yeah, well, this is what I just add by realizing that reality does have friction. Okay, so I will go over to an equation which does have friction inserted, but this is not in the discussion here. Now, to understand this from a, say, conceptual point of view, let's assume that we go one step back. We have this basin with vertical sidewalls, and now we are considering what the effect is of adding fluid. 3 parcels of fluid, colored differently here, and to see what the effect is in the basin, right? So we don't see the entrance, but we assume it's being added successively. And when we add the same amount of fluids, clearly the change in the sea level is the same in the case that the walls are vertical. But if the walls are not vertical, like in this triangular basin, clearly it depends on the previous water level, right? What the effect of the addition of mass is. Initially it's quite large, and then it gets less and less, right? So it's very simple to understand why you have this memory of the previous state of the elevation. And that's why you get really a forced nonlinear oscillator, which you need to consider. So, to go back, let's assume that we can continue with this assumption, and after scaling, making the variables dimensionless, so we scale the area with A0, we scale the volume with A0 times H and zeta with H, right? So I skip that here. So in the end, A is just 1 plus Z. Meaning at Z is minus 1, we have no water in the basin. At Z is 0, we have 1. Okay, we have area 1. Why do I take this? Well, because we can now actually become more explicit, right? We can put it in here, 1 plus z, so we integrate this. We get integrate between 0 and zeta, and we get zeta for the first term and a half zeta squared for the second term. And so we can also invert it. We can solve this quadratic equation and get zeta as a function of v. So it looks like a very strange equation, right? This nonlinear restoring term. However, if we look a little bit closer, we see that if we make a Taylor expansion of this square root around 0, that fortunately this term 1, which is so strange, is cancelled by this one, right? And you get indeed a half times 2v, so you get the linear oscillator back in this Taylor approximation. So no problem. So it gives some confidence that it might be correct. Here we have the tide at C, and now I've added the frictional term ad hoc, okay? Just knowing that I cannot do without friction, and in this case a linear type of friction. Now, if we for the moment neglect these terms, the forcing and the dissipation, it turns out this equation is solvable in special functions. What's interesting is that in the limit of large nonlinearity, that means that the basin empties when it's at low water, that in fact these special functions reduce to a set of coupled parabolas. So rather than finding a sinusoidal response in the basin, like we expect in a basin with vertical sidewalls, we get something which goes like this, right? It has very short-term low waters and very long period high waters. And well, if we reinsert the forcing and the dissipation, in general, we have, again, from this field of forced nonlinear oscillators, we have the idea that perhaps there are multiple equilibria and chaos. And this has led to, say, an oxymoron, which is called chaotic tides, right? Because the word tide in my language is tijd, means time, periodicity, right? And we see that from the outset we should expect perhaps to find chaos in it. And this is actually the challenge to us as observationalists in a coastal in coastal oceanography, to reconsider the observations we have from this point of view, because we have been taught, right, to look for the regularity, the tide, okay, but we forgot that in fact there may be chaos lurking behind it. And so I will go on and show in what sense this can actually happen. But this is kind of summarizing the main idea. So what it may lead to is that when you describe the amplitude response of a Helmholtz Bay, like one of the bays in the Wadden Sea, or perhaps the Norwegian fjord I was talking about, that when we describe it as a function of what's called a detuned frequency, it's detuned in the sense that we subtract the Helmholtz frequency and we scale with the Helmholtz frequency. So for the linear oscillator, we expect to find a strong response near resonance at this G detuned frequency equal to 0, right? But because it's a nonlinear oscillator, you see that the maximum response is having a detuned frequency which is actually larger than the Helmholtz frequency. It's positive. And indeed, for large amplitude oscillations, you see that it's actually showing an overhang. The resonant response is like a hardening spring. It's having a response which can, for a certain frequency, actually show multiple equilibria. What does it mean? Well, it means that one and the same forcing, the tide at sea, might, depending on the history, the way that the response is being reached, might actually, in theory, right, approach either an amplified state, more than 2.5 times the magnitude at sea, or a choked state, like in a lagoon, right? And these two occur together for the same frequency. It's a mystery, right? But it seems to be suggested by this. I should note that the intermediate intersection here is unstable, so I'm not going to discuss this. But these two states are stable. And this, again, has a world of connotation with it in the sense that it depends on the way that your frequency is changing. And I don't know exactly how to interpret this, because it suggests that the Helmholtz frequency is going to change well, then you're following this line until you're sitting here, and suddenly you go from a choked to amplified state. I think it's best to think that environmental conditions, right, can change. Like for instance, the average depth can change due to mean sea level rise or due to river runoff, right? That may affect such a change in this frequency here. And we should anticipate that maybe in records, a basin response can suddenly jump from being choked to being amplified, and back if you're going to hit this point and increase the detuned frequency, and then you fall down on this curve.
Excuse me.
Yep.
Just remind us, what are the multiple curves there?
These are for different amplitudes of the forcing.
Okay.
So the linear regime is sitting over here, right? Invisible. I haven't plotted it, but this one already, well, it may already have an overhang, but for linear curves you would expect a symmetric response, which shows resonance and amplification. Now, does this occur? Well, we tried to observe this in a laboratory experiment. So here is the setup in the lab. It's a bit messy, but here you see what we call the sea, and this is the estuary or the basin. It's communicating with the sea through a sea strait, and the basin has sloping sides, just to conform with what I was describing. So it has a side like this. And then here are two results. If we look at water height responses inside the basin and outside, well, outside the basin you see you have a regular forcing, because that's what we do here with this block of lead. It's being going up and down, and the water which is below it is being pushed below the estuary into the sea. So the sea is going up when this is going down. The sea is driving water through the sea strait, okay, sea strait. And what you see outside the basin is this sinusoidal response, which corresponds with what we choose for the forcing. Inside the basin you see something which has the characteristics of coupled parabola that I was mentioning, right, with prolonged high waters and with brief low waters. So this is one type of response. You see that the amplification is not really very dramatic. It's maybe a factor 1.5 or so. But in other cases, we see that we can reach amplifications up to factor 8 here. And indeed, you see that the response curve is showing this overhang. And experimentally, we see that there is this gap which carries the suggestion that we have just reached multiple equilibria, meaning that we have the coexistence of multiple states in the lab. Not very convincing, I must admit. So this is where this demonstration in the lab ends, and we are searching for opportunities to actually perhaps modify some of this to do reach this multiple equilibria in the laboratory, to help us envisage situations in the field, right, which may actually also show some of this. So is this parabolic shape that we found in theory and observed a little bit in the laboratory, is this far-fetched if we look at real observations? Well, this is an observations from the NIOZ jetty. So next to the institute, we have observations in blue and harmonic analysis prediction in green for spring tide. And if you superimpose coupled parabola, it doesn't seem too far-fetched to actually state that the presence of these flats, these tidal flats, may actually have been important for the response that we actually observe.
Those blue curves, however, just show large M4.
Yeah, well, you can, of course, Fourier analysis.
That doesn't tell you what's going on.
Yeah, it's true. Yes. So they do show M4 and probably also the other higher harmonics. Yes. And it's a mathematical way of saying, well, this curve has structure. I think what's interesting if you make that statement is that there is a distinct phase relationship of these superharmonics to the fundamental frequency. And that's because they need to be in phase in some sense to create these parabola. Yeah. So in a later study, which was done with another student, we looked at secondary oscillations in a small bay, which is called Mok Bay, and it's actually next to our institute. It's very small, of course, right? The Wadden Sea was already small. This is still small, okay? It's just barely larger than our lab, okay? But anyway, we had the opportunity to put in ADCP and some other instruments, optical backscatter and CTD. And this is a nice aerial photo which shows you the extensive presence of tidal flats plus a channel. And we had measurements at the beginning of the channel and at the end. And so what I'm going to argue is that during low tide, what we are looking at right now, right, that of course the water is restricted to this channel, and the eigenfrequency of that channel is very different from the one that you have when the water is covering this tidal flat, right? This is obvious. And in fact, if you look at this, it's clear that this so-called simple example I was giving with a linear slope is actually has the potential to be made still simpler, namely by having a Heaviside step function in terms of the area covered as a function of height, right? So below a certain level, the covered area is very small, and then suddenly it rises, right? So it's something we overlooked in the beginning, but this is actually still simpler.
So
and
if you back up a little bit, where was the ADCP located?
Here,
Oh, right at the mouth?
yeah. And here we had height measurements, and here as well, and here as well. Now, if we look at the secondary oscillations in Mok Bay, they are present, but we have to amplify the result by 10 to see it really clearly. That's this solid curve. So what these other curves show are the oscillations at the entrance, which is the dashed line, and the observations at the back of the basin, which show these wiggles, these secondary oscillations. And again, they are really quite small, right, in physical terms, or 1 centimeter. But I was giving you the argument why it might still be important for the exchange of water. And if you analyze the water level as a function of frequency, you see that indeed you can see these two distinct peaks associated with the low state of the water, which has this narrow region available, and the high state. And it leads to these two frequencies. So in terms of the velocity, we see also not as spectacular as in the fjord case. We see these variations in the flow, which are of the order of 10 centimeters. So it's an order of magnitude less than we saw before. So this has led to say still simpler version of the Helmholtz model, in which we have this bathymetry now, small area, large area, leading to two frequencies. And the idea is that that you now have a possibility to look at it from this perspective, that when the water is below this transition, right, it is the elevation is governed by a forced and damped linear oscillator having the Helmholtz frequency associated with the smaller area. But if the water is above that level, it's also governed by a linear oscillator, but then with a larger area. So basically you have a forced and damped linear oscillator, which all of us have been looking at during say the first years of our study, right? And we think it's a bit boring because well, we had to compute the response, and we saw that basically in principle there is a response at the forcing frequency as well as at the eigenfrequency, right? But that once you wait long enough, since the eigenmode is not fat, right, you only see the response at the forcing frequency. Okay? That's what we know about, say, a forced and damped linear oscillator. Okay, so eigenperiods are present and describe something about the initial state being damped out, but the forcing is determining the actual response. Now this is different here because the tide is changing from high to low water, and so it's basically bringing the oscillator for a while in one state in which you see that the eigenoscillations slowly decay, right? And then suddenly moves to another regime where the water level is low, and then you get the other oscillator being forced, right? So in other words, you get a continuous presence, the persistent presence of transients. And this may be responsible for these continuous presence which Honda observed in the elevation as a function of time. So a sudden change in system parameters causes these oscillations. It has the same implications, namely that, again, there is a possibility of chaotic response, and I think the relevance of it is that it's possible that it's influencing the transports through sea straits and making, say, the basins more healthy because of the increased transport. Okay? So this is basically the first part, and I would like to show another part which I cannot escape because all what I was speaking about was about homogeneous fluids, right? But we know that in estuaries that we might expect stratification to be important. So if you indulge, I will say a few words about this based on other observation by another student, Sjoerd Kroeskamp, who's presently at Le Mans. And we have this nice satellite photo, space shuttle photo from an astronaut who's looking down on the Wadden Sea. So here's the Institute NIOZ, and here's the Mok Bay that we talked about. And here you see two of the tributaries to the Marsh Deep, which is the tidal channel. Now, our institute has been working in this field for over 100 years, and the general perception was that the tides here are so strong that no matter when you go to the sea, it's always well mixed vertically, right? Because of friction. There are changes, of course, in the density if you move horizontally, so if you move further into the estuary, but there was kind of consensus that was not the case in the vertical. So, looking at pictures like this, you get another perception. First of all, I should say this is an artificial thing. This is mussel seed installation, as they call it. They grow mussel seed, right? So don't think of this as a physical phenomenon. But other features like these bands and these regions here in particular suggest that perhaps there is also a possibility of internal waves to actually exist. And indeed, coming back from holiday one day, we saw these lines, which are very clearly suggesting that they are surface manifestations of internal solitary waves. And later observation by Sjoerd was confirming this here. And so he made observations from the mooring that was displayed in the satellite picture. And he showed that indeed observations tell us that there can be internal waves, especially at the turn of the tide for a couple of hours. And it seems that you can get clear signs in the vertical velocity, for instance, or in the acoustic backscatter, such that if you zoom in on this, that here's the vertical velocity, and here is the long wave velocity. You get a very clear signal of an interfacial solitary wave, which we are speculating might perhaps be generated when the velocity differences across the interface are actually of the same order of magnitude as the phase speed of the waves. So, to summarize, we have seen that in simple models that coastal resonance tells us that bathymetry, the shape of the bathymetry matters, and that the presence of tidal flats may distort the tidal response, especially giving rise to short low waters and long high waters, and I'm very interested to hear what you find here in this area, right? Because I don't know anything about it. So it will be interesting to talk about it. We also observed that in theory one might expect under certain conditions the presence of multiple equilibria. Same forcing leads either to a macro or to a micro tidal response. And it's again of interest to look, for instance, at older records, geological records, to see if any evidence of a regime change can actually be found. Right? Are there periods where, for instance, there's a lot of sedimentation and other periods where there's not? So when there's almost no tide or when there is a tide. And we saw that we may expect to find a chaotic presence of short period eigenoscillations still produced by the tide but at a different time scale. And this is what I was alluding to in the beginning when I said there may be actually a response which is different from what we know about resonance, namely that the frequency matches the tidal frequency. Here the tidal frequency is important in kicking the system from one state to the other, but really the response is at the eigen oscillations. But they are reinvigorated every time the tide passes this particular level. So it has to do with a combination of having the appropriate geometry and the fact that the eigen oscillations may be produced by tides. And for the last example, we saw that during the turn of the tide, the stratification allows for internal solitary waves, presumably created by transcritical resonance. So to go back to the motto that I started out with, it seems that considering simple models, that they can talk to complex models, right, to numerical models, and ask, can you see the same thing, right? And if not, why not, right? And so it helps in finding interpretation of what might otherwise be just a result of the model, and you say, well, it is like it is, right, without really understanding. And I think that applies perhaps even more so to field observations that we want to make sense of. Thank you.
Short low waters and the long high waters, always thought kind of it's the bottom friction which kind of plays part more than, but you are turning things around.
Yes.
How do you reconcile between the former and your?
Well, I have no good conception about what to expect from the bottom friction, except that you know that if you look at the nonlinear friction, that you expect higher harmonics to be created, right? But
right.
in this case, where it's more like the restoring force, which has the nonlinearity, which is a first, say, different aspect, which is produced by considering a non-trivial topography. Right, that suggests that there is a particular phase relationship of those higher harmonics to the fundamental harmonic. Whether it's the same for the frictionally induced higher harmonics, I don't have a good feeling about that. Maybe somebody else.
Actually, that's one thing actually I want to comment on. See, look at the tidal response curve which you show, which is actually scaled, right?
Yes.
And when I was playing with some of those models there, I found that those scale speeds actually really come up from the quadratic formulation of the friction. Yeah, the bottom friction part, which is usually formulated as a quadratic form.
Right.
And that really contributed to this the signals in kind of scale. When we put up that signals, the broad crest and the sharp top there. Yeah. So those, those kind of scale keys there. Yeah, that was actually come out from this nonlinearity put into the bottom friction. Yeah. And maybe I should think about.
Well, I just had a quick, considering this curve, especially the blue curve, that older work by Aubrey and Spear, where they looked at the effects of intertidal storage in the
Mhm.
flats. Similar continuity and momentum ideas
Mhm.
showed that when you have intertidal flats, you pick up M4 constituents.
Mhm.
And so it just determines the basic structure of the tidal response.
Mhm. Yes.
So, is this consistent with those, those old papers by Aubrey Spear?
Yeah, I know of the papers, but not exactly what they state about, say, the phase relationship of the high harmonic to the fundamental harmonic, and whether it leads to a response which is similar to this in the sense.
Yes, it leads to flood dominance.
Okay.
And strong currents on flood, and then a long F.
Yeah, but this is in terms of sea surface elevation. So is it having the same? Because you're speaking about currents, right? And
I am.
yes.
Yeah.
So this is something to look into, I think.
Yes.
I have another quick question. So what determines the eigenfrequencies of these?
Yeah, it's the geometry of the basin, basically.
But they're so short.
Yeah.
They're-
Yeah. That's why the eigenfrequencies are usually quite small. And that's why the oscillations that you saw, for instance, in the Mok Bay are really very fast, right? And so you think insignificant, okay? But accept that you have to reason about the significance or insignificance on the basis of the height difference of such oscillations, and compare that to the height differences which the tide has. So what is the tide? The delay, you could say, between the external and the internal tide, the tide within the basin. If that is at any given moment the same difference in height as the secondary undulations have by themselves, which are presumably absent outside, right? Then you may expect to find considerable modification of the currents and therefore of the exchange.
Last quick question. In your laboratory experiment, did you actually, I couldn't quite see the inlet, but there's a tidal inlet there,
Yeah.
and then a basin.
Yeah, there is.
Mimicking a Helmholtz type of setup.
Yeah, it is, yes. So here there is a pipe, which you see, right, which is half submerged,
Yeah.
and that's the inlet. So we made it like this, yeah.
Okay.
Yeah.
I actually have 3 comments. One of the things we do around here is look at the flow of water up across the seafloor. So the groundwater on the land is high, sea level drops, it drives a flow through the aquifer up across the seafloor.
Yeah.
I've often thought that these measurements are showing some nonlinearity, and they're terrible. And usually I'm talking to geochemists, so they don't care one way or the other. We have been attributing it to satiation,
Uh-huh.
but this process may be driving that modulation of flow across the seafloor, not only in and out.
Yes, yeah, it's a very good remark, yes.
The other, long ago, I had in Long Island Sound, which is out here, one of the things you see in the sediment column is a change in dynamics somehow. You see a change in the sedimentation.
Right.
And a long time ago, I had a student looking at the Helmholtz resonance of Long Island Sound at base of rising sea level.
I see.
He left and I stopped.
So
But there may be something there.
You leave us in suspense.
So I don't know the answer.
No.
Last comment is we had seen in ADCP records, we had actually seen those internal waves, very much like you showed in the
Ah, yes.
Hudson River.
Yeah. Yeah, I expect that you find those here in a much richer fashion than we were able to
Yeah, they were
to find.
spectacular.
Yeah.
By the way, Henry, the tidal signal, the water level in the Flex Bay, you showed me some time ago.
Flex pond.
Yeah, Flex Pond, not Bay. Does that actually show this kind of, the asymmetry between the flat and ebb, the peaky one and the broad one? Remember you were showing me that?
Yeah, it is asymmetric.
Yeah,
I don't
yeah.
know. But it's probably,
Yeah,
it's the right situation, big
Yeah,
flats.
that's right, yeah. So I was actually curious about whether this had something to do, with this kind of nonlinear effect.
But we've done a lot of work in Stony Brook Harbor, which is a local embayment
Yeah.
that wets and dries.
Uh-huh.
And you see very strong flood dominance. The tide goes up quickly,
Mhm.
and then it ebbs very slowly as the flats are exposed.
Yes.
And we just do simple harmonic analysis, and again show very strong M4.
Yes. Yeah.
That can explain that.
Yes. Yeah, so I know that looking at signals from, say, a Fourier perspective or harmonic analysis perspective is quite common, right? But
Yes,
what I try to advocate is also to perhaps have this physical picture.
Yeah.
And so in that case, right, of the phenomenon you describe, right, might perhaps be also interpreted in another way.
Differently.
Yes, and I think if you go back to what it tells us about the classical approach, right? It tells us that there should be some type of phase relationship between these components, and also a certain amplitude relationship,
Yeah.
which is not, say, random, not just the result, right? But which has a meaning.
Oh, it's definitely fixed.
Yes. Okay. Yeah, and I don't know how to interpret it, but I think this is the challenge which is poses to us, to think about this in a kind of coherent way, right? Because as I said, if you want to describe this by Fourier terms, right, you get them, the high harmonics, but in a very distinct way. Yeah.
Yeah, this is just a comment, almost similar to what Henry had given. I remember, this is way back, almost 20 years ago.
Yeah,
we were going across the Hudson River, rather than going along, just doing a lot of sections
Yes.
across. And what I remember the ADCP records showing to be, yes, nice, you have this nice sinusoidal curve, but at the high speed, that's when you see these little wiggles.
Ah, yes.
But for the low one, there wasn't. And I remember Don Ping asking me, why is that? And so first I thought maybe I didn't get the calibration right.
Noise.
And I'll do all the calibration, and I knew, but we'll go back and get the same thing.
Mm.
What is puzzling me now, and now it's kind of, I'm connecting, maybe I should go back to that later. What I'm wondering, why it never showed for the lower one?
Yes.
Because it should, but you would think it should show for both,
Mm.
not just.
Yeah.
But on the other hand, that nonlinear usually break the symmetry. So that means that it may not naturally equally show up in both the flat and the amp. But typically nonlinear break the symmetry.
Right.
Yeah, maybe true. Yes. Yeah.
And another thing actually, this is also I like to make a comment that those high harmonic, right? If you just look at the elevation, when you see all those teeny little bit wiggling, it doesn't really matter because only like 10 centimeter, right? But in terms of the momentum or in terms of velocity, and for the harmonics, right, it's always amplitude times frequency. So therefore those higher harmonic oscillations, the frequency is so high, so therefore the velocity associated with those fluctuations is very big.
Yeah.
Yeah, that's why that in the other plot you show that you see those high peaks when
Yes.
you look at the velocity, but then the surface, when you look at the surface, those teeny bumps.
Mm-hmm.
So it could be misinterpreted in that sense.
Yeah. No, that's true. Yeah.
Know where to look. Yeah. Any more questions?
General comment. In a natural system, it's often very difficult to define the inlet length and
Yeah.
depth.
Sorry, the inlet?
It's very difficult to find the proper length
Oh, yes. Yeah.
and depth and width.
And the width.
Yes,
Yes.
It's very, very difficult to define that.
Yes. Well, I think it is appearing as a lumped parameter in the
Yeah.
theory, meaning it has just this single expression. Oh, here it was, right?
GH.
Yeah. So the gravity, depth, the width of the connecting channel, and the surface area, and the length of the channel.
Yeah.
So if you don't know one of them precisely, right, maybe you can look at this.
Yeah.
And I think this should show up in the same sense as the experiment in the Mok Bay was showing these peaks, right? It's a challenge to look at the time series measured in these basins, and then see if there is a distinct peak which is telling you this is the eigenfrequency, Helmholtz or quarter wavelengths. Yeah.
Yes.
Okay, any more questions? All right, then let's
Thank you.
I understand that we have lunch there, right? So you, what? No, it's the other room there. I was told there's a lunch.
Is it in 113 or
I think Steve told me that there's a lunch.
which room?
So, what?
Which room?
Uber room or?
I will assume it's
Probably,
room, right? Yeah, so we can see someone is coming over there.
Then you got a real job.
Basically like station.
Yeah, well, yeah.
So therefore, he excited by having a green lake. He's also excited by having some interesting change with groundwater.
Well,
Basically, it's about how you
Claudia.
No, the exchange per hour is got to. You see the response.
Yes.
Because it's the water runs in the land is here and the water on the open ocean is here.
Yeah.
This